Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of high-performance computing. We'll dive into key concepts like shared memory parallel programming with Open MP, parallel execution, data scoping, work sharing using loops, synchronization, reductions, loop scheduling and tasking. Let's get started. Slide 1. Introduction to Shared Memory Parallel Programming with Open. Let's start with Open, a widely used API for shared memory parallel programming. Shared memory systems are those where multiple processes or threads access a common pool of memory. This is different from distributed memory where each processor has its own memory. Open works by adding compiler directives or special commands into your existing C, C++, or Fortran programs. These directives instruct the compiler to create parallel parts of the program, allowing multiple tasks to run simultaneously. Parallel programming is important because it allows us to divide large computational problems into smaller parts, making use of multiple cores in modern processes to solve them faster. Open supports multi-threading, meaning multiple threads work together on a problem, often speeding up computation dramatically. An important advantage is that Open makes it relatively easy to convert a sequential program into a parallel one, unlike MPI or other models that require complete rewrites. For example, if you are performing matrix multiplication, instead of one thread calculating all elements, multiple threads can each calculate part of the matrix, reducing time. Thus, Open helps achieve efficient processor utilization, making it highly relevant in today's multi-core world. Slide 2. Parallel execution in Open. Parallel execution is at the heart of Open. It allows multiple threads to run concurrently, which makes programs faster by dividing work among available processes. We use the directive pragma omp parallel to create a parallel region. This is the part of code that will be executed by multiple threads. When this directive is encountered, a master thread creates multiple worker threads. These threads execute the code in parallel and then merge back into a single thread. The number of threads can be controlled. For example, you can specify how many threads you want, or let Open choose automatically based on the system's capabilities. During execution, each thread may work on a different part of the data, such as different rows of a matrix or different chunks of an array. This makes the code run faster and utilize multi-core CPUs better, which is why parallel execution is crucial in high-performance computing. A simple example would be adding elements of two arrays in parallel instead of sequentially. Slide 3. Data scoping in Open. Data scoping determines how variables are handled in parallel regions, whether each thread gets its own copy or shares a common variable. Variables can be shared, meaning all threads access the same variable. This is useful when all threads need to update or read common data. But if not handled properly, it can lead to errors like race conditions. Private variables, on the other hand, are unique to each thread. A common example is a loop index variable inside a parallel loop. Each thread needs its own loop counter. There are also advanced types. First, private. Each thread gets its own copy initialized with the value from before the parallel region. Last, private. One thread's value, typically the last one, is used after the parallel region. Thread private makes a variable private and keeps its value between different parallel regions. Proper data scoping is crucial to avoid unexpected results and ensure safe parallel execution. Slide 4. Work sharing using loops in Open. In parallel computing, work sharing helps distribute parts of a task among different threads. Loops are the most common way to implement work sharing in Open because many problems, like matrix computations, are naturally repetitive. We use pragma omp to divide loop iterations among threads. For example, if you have a loop running from 1 to 100, Open can give 25 iterations to each of 4 threads. Combining pragma omp for the parallel region allows fine control over what is run in parallel. This prevents duplication of work and ensures each thread handles a different piece, which is crucial for performance and correctness. A practical example is dividing an array summation task so that each thread adds part of the array, and results are combined later. Work sharing makes sure all cores are busy, reducing total computation time. Slide 5. Synchronization in Open. Synchronization is necessary to manage how threads interact, especially when sharing data. Without synchronization, we risk data races, where multiple threads update the same data simultaneously, causing incorrect results. Some key synchronization tools. Barrier ensures all threads reach a point before moving forward. Example: all threads must finish computing their part of a sum before moving to the next step. Critical section: a block of code that only one thread can execute at a time, useful when updating shared data. Atomic: a lightweight way to ensure atomic, indivisible, updates to variables. Example: safely incrementing a counter. Master directive specifies that only the master thread runs a particular section. Locks: more manual way to control access to data using functions like omp_set_lock. These tools prevent conflicts and ensure correct results, but should be used carefully as overuse can slow down performance. Slide 6. Reductions in Open. Reduction is a special technique to combine results from different threads safely. For example, when you want to sum all elements of an array using multiple threads, each thread adds a part, and the total sum is combined automatically. In Open, we use pragma omp parallel for reduction operator variable for this. Operator can be sum, plus, product, max, min, etc. Reduction makes sure that each thread works independently on its piece and Open takes care of combining them efficiently. This avoids the need for explicit synchronization. For instance, if you are calculating the sum of 1 to 100, 4 threads can sum parts like 125, 2650, etc., and Open combines these results. Reduction makes parallel aggregate operations clean, safe, and efficient. Slide 7. Loop scheduling in Open. Loop scheduling defines how loop iterations are divided among threads. 1. Static scheduling evenly divides work before execution. Best for loops with equal work per iteration. 2. Dynamic scheduling. Threads grab chunks as they finish, useful when work per iteration varies. 3. Guided scheduling, like dynamic, but starts with large chunks and decreases size to balance workload. 4. Runtime scheduling, scheduling decided at runtime using environment variables. Choosing the right scheduling affects performance and balance. If work is uneven and static scheduling is used, some threads will finish early and stay idle. Dynamic helps avoid this by adjusting distribution on the fly. For example, when processing rows of a matrix where some rows take longer, dynamic or guided is better. Slide 8. Tasking in Open. Tasking allows dividing a program into small tasks, which can run in parallel. Instead of only parallelizing loops, pragma omp task lets us create tasks for any independent work, like recursive function calls. Useful when we don't know workload at compile time. Work units are irregular or dependent on conditions. We can use taskwait to wait for tasks to finish before proceeding. Tasking makes Open powerful for problems like parallel quicksort, graph traversal, or when processing hierarchical data like trees. It introduces flexibility to write more complex parallel programs beyond loops. Slide 9. Advantages and disadvantages of Open. Advantages: easy to learn and implement using simple directives. Portable and widely supported in compilers. Requires fewer code changes to add parallelism. Ideal for multi-core CPUs and simple parallel tasks. Automatic thread management. Supports dynamic workload handling with tasking. Incremental parallelism, can add parallelism gradually. Integrates well with C, C++, and Fortran. Good for loop-heavy computations. Disadvantages. Limited to shared memory systems, not suited for distributed clusters. Scalability issues beyond multi-core CPUs. Needs careful tuning for best performance. Irregular problems can be hard to parallelize. Complex debugging in parallel environments. Risk of data races without proper synchronization. Load imbalance possible with uneven tasks. Less control over thread core mapping.